Okay, this is the final one for today. Uh, we're going to talk about something that you probably already are familiar with. We're going to talk about bandwidth, emission designators, and an overview of some of the signal analysis equipment that is out there. Can everyone see the screen? I need to go to the slideshow mode. Okay, is that good? All right. We've already talked extensively about bandwidth, which is one of the most fundamental characteristics of any signal out there. Basically, the difference between the upper and lower frequencies of a signal of interest within a continuous band of frequencies can be measured in hertz, kilohertz, megahertz, whatever, depending on the application. So it's just a width of spectrum in the frequency domain. So I'm going to talk a little bit about emission designators, because these are a good way to classify signals. And you may or may not already be familiar with the various parts of an emission designator, but I'll go through them in case you're not familiar. So this is an international designation, not just an FCC thing. All over the FCC, the US and the FCC used to have its own system, but it gave way years ago to the international system. So you may see on some of the older licenses the old style emission designators, but given way to this new designator. So every type of emission gets classified according to its bandwidth, its method of modulation, the nature of the signal, and the type of information transmitted. So the key thing about an emission designator is it's based on the characteristics of the signal that goes out over the air. It has nothing to do with the actual equipment being used. So there are various parts of the emission designator. The first one is the part that characterizes the bandwidth of the signal. And in an emission designator, the bandwidth is expressed as 4 characters, represented by 3 digits and 1 letter. The letter is used in place of a decimal point and will immediately tell you what band you're operating in, whether it's an H, a K, an M, a G, will stand for hertz, kilohertz, megahertz, or gigahertz. So for instance, if you see an emission designator that starts with 500H, that means it's a 500 hertz signal, which is pretty low for a radio frequency signal, but nonetheless, more commonly we might see something like 2M50 and the M meaning megahertz, so we interpret that as being 2.5 megahertz. Is everybody familiar with these? So the second part of an emission designator has to do with the type of modulation. And there's letter characters from A through X that will describe the different type of modulation. So you look on the list, you'll see everything from sideband to TV, AM or FM, frequency modulation, phase modulation, band, pulse amplitude modulation, pulse width modulation, pulse position modulation, all kinds. And there are probably some that don't even fit these criteria, and that we give them an X for none of the above. When this was created, they couldn't anticipate all the different types of modulation there are, but we saw in the previous section that the primary groupings that we're dealing with will be frequency modulation, phase modulation, and amplitude modulation. So the third part of the emission designator tells us what type of signal it is. Does it have a modulating signal at all, or is it a dead carrier? If it's dead carrier, the symbol is 0. We talked about TDMA and FDMA. So you'll have a different type of signal, whether it's carrying one channel of information or more than one channel of information. So an FDMA signal will have a different third character than a TDMA. And you may have something that's a combination that has analog and digital channels. A television signal is a complex signal that contains both analog and digital components. So that might have a 9 in it. And the fourth part of the emission designator tells us what type of information is being carried. So is it data? Is it fax? Is it voice? Is it video? And if it's, they've left themselves an out in each case by having an X for none of the above, so that they don't have to add a letter for each new type of information that gets transmitted. So in most of the signals we're going to be dealing with here, we're going to see probably a D or an E. And the fifth part gives any additional detail are necessary to describe the signal. So these mostly apply to broadcast type emissions where they might be mono or stereo, commercial grade sound, grayscale or full image video. So we may not see this in the land mobile radio designator. And then the sixth and final part provides any additional information about any multiplexing that might be used. And here's where our FDMA and TDMA come into play. F for frequency division, for time division. We might have a combination of frequency and time division. And our CDMA for code division multiplexing, or code division multiple access. So let's look at some common emission designators that we might see. In the analog world, a couple that we might see would be A3E for AM speech. This is still used in aviation radio. They still use AM. So you might see an A3E for them. FM. Now, you won't see this in Part 90 much anymore, but and amateur and some other VHF, you might see an F3E. On the wide the wide bandwidth FM with 20 kilohertz bandwidth and 5 kilohertz deviation, you might see a 20 KO F3E. So that means with the 20 KO 0, it's a 20 kilohertz bandwidth, F3 for FM, and F3E. So we combine the bandwidth with the F3E. So things like the NOAA weather radio, the marine radio, some other types of users, you might still see 20 KO F3E. And then we have, we might see the narrow FM, 11 K2 F3E, narrow FM, 11 and a quarter kilohertz bandwidth. So this fits within the 12 kilohertz emission bandwidth with 2.5 kilohertz deviation. So this is narrowband FM. This is still not digital. Narrow FM. In the US, all Part 90 land mobile radio service users above 50 meg were required to upgrade to narrowband. So they could have done it analog or they could have done it digital. In P25 phase 1, the emission designator for the radios can actually do several types of emission, but the actual voice component of P25 phase 1 we might typically see is 8K30 F1W. 8K30 means it has a emission bandwidth of 8.3 kilohertz. The F means it's frequency modulation. Now C4FM is still FM. The 1 means it carries a single voice channel with data. And the W means it can carry a combination of data and voice. So with that one designator, we've provided a lot of information about that. For phase 2, we have more complex modulations with different emission designators. So the downlink signal in a phase 2 TD system, you might see 9K80 D7W. HDQPSK stands for Harmonized Differential Quadrature Phase Shift Keying, and that's why we don't spell it out. The 9K80 means it takes a 9.8 kilohertz bandwidth, so it's not as wide as the phase 1 signal. D means it uses a combination of FM and phase modulation. The 7 means more than one channel containing digital information. So that describes the fact that with TDMA, it provides more than one channel of information. And the W tells you it's a combination of audio and data being carried. On the uplink or inbound side, we might see an emission designator of 8K10 F1W. And HCPM stands for Harmonized Continuous Phase Modulation. So again, this is the inbound side of phase 2. The 8K10 means we have an 8.1 kilohertz bandwidth. F for frequency modulation. The 1 again means it carries a single channel with digital information. And the W means it's a combination of data and voice. Okay. So remember on the TDMA, it's the outbound side that's doing the TDMA. Okay. Here is DMR. What kind of emission does DMR have? So there's two different operating modes in DMR. When it carries data, it has one designator, and when it carries voice, it has a different one. The bandwidth's the same in either event. So when carrying data, it can be seen as a 7K60 FXD. So the 7K60 means it's 7.6 kilohertz bandwidth. F means it's frequency modulation, that is to say C4FM. The X means the channel is not designated for single or multiple channel operation. And the reason it's an X is that DMR can carry either voice or data, so we leave that one open. I mean, it can carry either single or multiple channels. So depending on what mode it's operating in, it can operate in TDMA, but it can operate in TDMA. So that's why this becomes an X. And D means it's carrying data. Now, if it's carrying voice, only one character changes, and the E changes to a D. So everything else is the same, except it's carrying voice, and the E means it's carrying voice transmission. So if you work a lot with these emission designators and see them frequently, and you read somebody's license, that emission designator on the license tells you an awful lot about what kind of being carried on that. And if you work with these frequently, you'll be able to immediately see what kind of signal is being described on the license by looking at the emission designator. Well, NXDN. Well, it has 4 different operating modes. It can carry data or voice, and it can operate in wide mode or narrow mode. So when it's in wide mode, notice the bandwidth is 8K30. So it has an 8.3 kilohertz bandwidth in wide mode when it's carrying um, the two signals. When it's in narrow band and it's carrying only one, it has about half the bandwidth, 4K0. So beyond that, the difference is just like with the DMR, a D when it's carrying data and an E when it's carrying voice. So because it has these four different operating modes, NXDN has four different emission designators. So any question on emission designators? It's a good way to describe the characteristics of a signal, and it's internationally recognized. And the final part of the presentations today, I'm just going to talk a little bit about some signal analysis equipment. And the equipment that I show here is kind of lab grade equipment. You may or may not use it in the field, but just to be aware of some of the equipment that's out there and what it can do. So the signal analysis equipment that I'm describing here is multi tens of thousands of dollars per unit, but it's very capable. It uses software defined radios, and uh, it can do a lot of different things, just like service monitors of years ago could do many things. These are um, analysis equipment that can do a lot of different functions. A vector signal analyzer. That's the device that can break out the various vectors in the signal and give you things like the constellation diagrams that will let you easily identify what kind of signal you're dealing with. A bandwidth monitor to see what kind of bandwidth you're looking at. A modulation monitor to identify what kind of modulation is occurring. What's the signal to noise ratio? The ability to put an oscilloscope on there with an eye pattern generator. And of course, a spectrum analyzer, internal signal generators, and constellation display. So there's a lot of different units out here. I picked a few. This one we use a lot in the field. The Anritsu, that should be 412E. This is a handheld signal analyzer, spectrum analyzer. I like it. It can identify things like P25, phase 1 and 2, DMR, Tetra, NXDN, DPMR, several other types of modulation. I can identify LTE, WiMAX, X is an inter analyzer, spectrum analyzer, antenna analyzer. It's used a lot in sweeping cables to identify return losses. Helps you to find passive mod. Is an internal power meter. And nice thing is only weighs 7.5 pounds and you can hold it in your hand. You may recognize this one. Viavi is the company that bought Aeroflex, and Aeroflex is formerly Agilent, which was formerly HP. So it's gone through a lot of different changes. Um, this is more of a lab instrument, has AM, FM duplex, can operate in Tetra, high performance data, which is the wide bandwidth, high speed data, spectrum analyzer, tracking generator. It's almost a legacy instrument because it's been reincarnated from the old Aeroflex unit. And it traces back to the Agilent 8920, which is this. There's a company called Keysight that that picked up a lot of the old Agilent products, and Keysight is really into software-defined radios and getting away from these kind of traditional instruments with the buttons and knobs on it. But this has over 20 different instruments in it. This, I don't even know if this one's still in production because they've really gone over to software-defined radios in its place. Rohde and Schwarz, which is a German company, has a signal and spectrum analyzer. You can see it. Most of the instruments now have more screen real estate and less of the buttons and knobs. Uh, Everything is done in software with the ability to operate with computer applications. And you see it's based on Windows 10 system. So what used to be really um, test equipment is now more software application than anything else. Tektronix version of a vector system analyzer can operate in the frequency and the time domain. And here is a typical example of a software base. I think this is Keysight 89600 PSA software. And you can see they're really into color displays. You can get spectrum, you can get time analysis. You can see in the upper left, that looks like a 16-point constellation. They're looking at a 16 QAM signal here. So that's the kind of information and analysis you can get. Again, this may not be the type of equipment you use in the field, but these are some of the lab grade instruments that can do real detailed signal analysis. And with that, I'm pretty much done with my last slide.